Thanks for being here. Welcome to our talk about Dig Smart, create a reliable cloud-native DNS service. Who in the room has ever experienced a DNS outage? Please raise your hand. So, yeah, it's fun, right? We're talking about how you can make DNS a bit more reliable, how you can build a cloud-native, reliable DNS service. My name is Studler. I'm a DevOps engineer at Swisscom. I'm here with Fabian Schulz, DevOps engineer at Swisscom as well. We're part of the same team building the cloud-native 5G core in Swisscom. I don't talk about Swisscom here today because I assume you know it. This talk connects a bit to a few topics around GitOps, around Kubernetes, Kubernetes resource model like KRM. If you want to know more, please check out these links. And we will now continue with the DNS itself. So DNS in 5G core, that's what we're building here. What does it mean? So first of all, it means private zones. So we're talking about very specific private zones that are only consumed from within the 5G core itself. That also means that there's only moderate throughput, so it's not millions of requests a second, which you have with a public-facing, internet-facing DNS service. It's only tens to hundreds. And a very hard requirement is the lowest latency you can get, which is very important for the mobile network because it's affecting the mobile network performance heavily. So this leads us to a few requirements. We've identified 6 different requirements for this specific DNS service. First one is proximity to the consumer. So we cannot have a SaaS offering like Route 53 or something because it's too far away. Then the second one is it needs to be fully automated. So we cannot have manual interaction. So we cannot have someone click in a UI. So that's not what we want, right? Then it should be geo-redundant, which means we should be able to spread across multiple geo-regions, so to say. So we cannot have singletons. It should be distributed as much as possible. Then we need advanced features of DNS. We cannot just have A and C name records. It should include stuff like SRV records, NAPTR records. I don't know if you heard of that, but it's fancy stuff in the DNS server that can do some kind of magic to serve DNS records, for instance, for SIP phone calls and so on. Then we want to integrate into Kubernetes with external DNS. So we not only limit us to REST API, we also limit ourselves to the Kubernetes API itself. And then last but not least, we should reduce as much as possible the ability of failure or the potential of failure, so we should have a minimal amount of single points of failure. We will see that in the design later on, and that Fabian will show, which is quite interesting on our architecture. So that's the scene, so to say. On this picture, you can see the full thing we're showing today. So don't panic, don't leave the room just yet. It's a bit overwhelming. We try to break it down as much as possible for you. This picture shows 2 clusters on the top and on the bottom. Maybe important to say, there's a legend that's too small now. Yellow boxes represent DNS agents, DNS servers, basically. Blue boxes represent DNS consumers. And then there are arrows in between that Fabian will show you later on. We also have a Git repo that where these resources are published, so you can take your time later on if you're interested to dig into it. So we're going to cut that in half to start with, and then I'm starting with the built-in Kubernetes DNS service, which consists of a few components. On the bottom right, you can see the Kubernetes DNS service itself. It's a core DNS instance. And we also, in the bottom middle, we have a node cache. That's basically optional. It's not really relevant to our design. You can have it, you cannot have it. It will have an impact on speed and performance and so on. And it's a cache, so it brings its own dangers, right? But in the end, we don't talk a lot about that one today. It's part of the Kubernetes ecosystem and documentation. So assume we have a pod that wants to know the IP address of a service. So this pod will do a DNS request to its default name server or name server configured in the resolve conf, right? This request will eventually arrive on the DNS service of Kubernetes, which is this core DNS instance, and it will check the kube API whether there is a service with that name or not. If there is a service with that name and it has an IP, it will return this IP, and the consumer will be happy. So the technology used here is core DNS. It's a CNCF project. It's standard for Kubernetes, so every Kubernetes cluster deploys one core DNS instance, even the local kind cluster. And it's using the kube API as a backend, so it's completely stateless. It's just serving whatever the kube API contains. So the feature is simple. It's enabling in-cluster service discovery. What it doesn't do is exposing anything outside of Kubernetes, so it's only within the cluster scope, and there are now custom resource records, like you cannot create your Amex record or your Napster record or whatsoever. So this means we need another service for that. There are some more resources about the Kubernetes DNS. You can check that out later on. So we have a few requirements for this new DNS service. We call that the authoritative service, DNS service. We have shortlisted 3 different tools or technologies. So first one is core DNS. That's the same that Kubernetes uses. Second one is Power DNS. It's a cloud native-ish DNS service or DNS open source DNS tool. And the third one is Route 53, which is a SaaS. You can put whatever SaaS you want there. It's more or less the same. So when looking at the 4 most important requirements, the first one is integration into external DNS. That's given by all of them. So external DNS is the tool for automating in Kubernetes. So that's good. A and C name record creation. Also, all of the solutions can basically provide that. It gets trickier when we talk about more advanced DNS features like Napster records or even TXT records and so on, because their core DNS cannot support that. It's because one of these core DNS plugins that you traditionally use doesn't actually support anything else than A and C name. And for Power DNS and the SaaS offering, we were able to solve it in external DNS. We had to implement a small fix, but this now works for both of them. And the last requirement, it's the obvious one, proximity to consumer, which limits us to not use SaaS in the end. So we have a clear winner, which is Power DNS authoritative server. So that's the tool we're using. If you look at the diagram and zoom out a bit, you can see on the right there's Power DNS, which will now be shown by Fabian.
Yep. All right. So now I'll show you where we put Power DNS and how we automate this. Let me change to a pointer so everyone sees it. All right. So here you can see now our deployment. Here's the DNS namespace, and here you can see the external DNS deployed and the Power DNS deployment. Now, so what does external DNS do? Oh, sorry, zoom in. What does external DNS do? So external DNS watches certain resources. So in our Kubernetes cluster, it watches the resource of type DNS endpoint. This is a specific resource for external DNS, which I will show you later. But the nice thing is it also watches other resources, such as services, load balancer, or Istio gateways. And on these resources, it looks for annotations. And with these annotations, it will know the domain name and can then automate the creation of this in Power DNS. So now let's come to the first demo. In this demo, I want to show you how external DNS watches over these resources and then calls the Power DNS API to add the resources there. So let's exit the presentation. So on this machine, I have a local kind cluster running. On the top, you can see K9S, and most of you probably know it. It's just a terminal GUI using a kube control. And we can see here, we are in the DNS namespace. You can see here, I'm listing the pods. And here we see the 2 pods, the external DNS and the Power DNS deployments. Now, let's go to the first demo. Here, now, I have a service YAML. So in this service YAML, you can see I have a simple Nginx deployment. Here we have the Nginx deployment. And then we have a service. And here in this service, you can see I added an annotation. And this is the external DNS annotation where I define the host name. So here I defined nginx.5gc.3gpnetwork.org. So let's apply this to the cluster. Now you should see in the top we have the Nginx pod that comes there, that arrives there. And let's have a look at the services. So now you can see here our Nginx service. What's really nice is here at the bottom, you see I just have an annotation. I don't have an IP address. Here, of course, now the load balancer assigned an IP address to my Nginx service. Now let's have a look. Let's go back to the pods. And so we have the external DNS. Let's look at the logs of external DNS. And in the logs, you can see that it constantly checks what files, what resources are there. And here you can see it found this resource. So it did a create command to write this into the Power DNS. So let me get my notes. So I'll show you the link later. We have everything public on our GitHub, where you can see all the steps and also recreate this. And I use this to get my notes. I don't do so many typos. So what do I do here is I just do a kubectl execute. So I call a dig command where I search for this nginx503gp.org. And here I define who to ask for. So if you go back to the services, you can see here that the Power DNS service runs on 1096.0.12. So I ask 1096.0.12. And you can see here I get the response. So I have my domain name and I have the IP. Now, here I have another type of resource, which I mentioned before. This is the DNS endpoint CR. So you can see this is of kind DNS endpoint. Here I define a name. This is a CNAME record and the target. So just to show you that nothing is there yet, let's already try and query this. So endpoint 1. I query and there's no response, just so you see that there's actually nothing there yet. So now we apply this new resource. Here at the top again, I can list, for example, all the DNS endpoints and all the namespaces. I can see it's there. Now let's go back to the pods of just in the DNS namespace. We can again look at the logs of external DNS. We can see that it did the create. So now let's do this dig again. And you can see now it's there. So here this demonstrated now the automation. So this is the end of the first demo. I'll just need to prepare the second demo in the meantime. And then let's go back to the presentation. So now that we've seen this automation, we have to look at, first, I need to show now one of the advantages. There's one slide which we just added, so that's why I'm not used to this one. So you can see, here's how it looks in Git. So the nice thing is when you put this in Git, the service, there is no IP. So we just define the DNS. And then you add this to Kubernetes, and in Kubernetes, we then have an IP address which has been added, and this then creates the entry. So what's really nice is we don't want any IP addresses in our Git. And this helps us to automate the whole thing, that we don't have IP addresses in our Git, but we still have the DNS entries. So now we come to the forwarding part. So we want to connect those two worlds. So we have on the left the Kubernetes, and on the right side we have our DNS namespace. So for this we add a forwarder. Our forwarder is a core DNS deployment. And what we do is we define in the Kubernetes core DNS, we define that we want to forward all traffic to our own core DNS. And our own core DNS will then do the triage. So it will forward all requests for the 5GC domain to our Power DNS instance, and all the other requests will forward them to the Swisscom DNS or any other internet DNS. And this core DNS forwarder also has an external IP, because there's external consumers, so also of the 5G core, but which are not within our Kubernetes cluster, they can also access it. All right, so let's have a look at the second demo about forwarding. In the meantime, we can see what has changed. So you can see here 90 seconds ago, we have a new core DNS deployment. So this is this new core DNS instance that I put there. We can list, for example, now the config maps, because the config maps, it's what's kind of the configuration of this core DNS. So if I go to the config map and I describe it, so we have a look at it, we can see that in the config map, I have a forwarding of the 5GC domain to 10.96.0.12. If you remember from before, that's our Power DNS instance. And all others, the dots, they get forwarded to the 1.1.1 DNS. The other thing that has changed is, as I said, there's another core DNS in the Cube system. So here we're in the Cube system namespace. There's also a core DNS, and here it's config map. And if we have a look at this, we can see that all Kubernetes resources get first forwarded to the cluster.local. Then we forward everything else to 10.96.0.11. And this is now our new core DNS. We can see this if I go to the services in the DNS. You can see here 10.96.0.11. So here we have our core DNS. So what changed to before is, remember before I did the request with here the Power DNS. Now I can remove this, do the request, and I get the answer. And I can also, if you want to see from where it comes from, instead of using a dig, I can also do ns lookup. And then you can see that this response comes from this 10.0.10, and this is the core DNS service in the Cube system namespace. Let me go quickly to this demo page. All right, we have everything. Then let's prepare for the third demo. Go back to the slides. All right, so now you've seen how this works with one cluster. We'll continue now with a second cluster. So now let's add a second cluster at the bottom. You can see it's exactly the same. They're completely decoupled. It's exactly the same. So the second cluster, we call let's say the bottom cluster is the Zurich cluster and top is the Bern cluster. And the bottom one has its own external DNS, watching its own resources and writing in its own Power DNS. And they all have their own database. So because we don't want a mix of databases or something, so they have their own records. So now we want to sync them. So to have them synced, we first create a second external DNS in the Bern cluster. This, of course, watches the resource in the Bern cluster, but now it calls the API of the Power DNS in the Zurich cluster. So, which means that in the Power DNS instance of the Zurich cluster, we also have all the resources of the Bern cluster. And of course, we want this the other way around. So we add another external DNS in the Zurich cluster, watching the Zurich resources, which calls the API of the Power NS in the Bern cluster. So now we have a setup where we should have the same resources, the same records in the Power DNS of Zurich and Bern. Now we want to leverage this. For this, we need to set up, for example, fallback routes, because we want to, if something happens, for example, to the Power DNS in the Bern cluster, we want to use the one from the Zurich cluster. So for this, we add fallback routes. So what that means, if our core DNS forwarder cannot reach its own Power DNS, it will try to reach the one from the other cluster. And of course, this also goes the other way around, because we want redundancy both ways. And then there's one more redundancy we'll add, is in case we have some misconfiguration or something in our DNS namespace, and let's say something here or this forwarding doesn't work, we add a fallback, a default fallback in the core Kubernetes, in the core DNS of the Cube system namespace, just directly to an external DNS after 2 seconds. So the idea is that in case something is broken, we can still access the internet and try to fix the issue. All right, so now let's come to this multi-cluster demo setup. I'll open another K9S window here. Let's move this a bit. So you can see now at the bottom, here you can see is the context in the cluster is kind DNS1, and at the top you can see it's kind DNS0. So you can see I have 2 local clusters now running. Let's also at the top one list the pods. What has changed in the top one, you can see here 100 seconds ago we got a new external DNS. So this is the new external DNS instance. And if we look at the logs of this new external DNS, you can see that it started up and then it found all these resources like our endpoint, our Nginx, and it actually synced them to the second one. And we can now try this out. So let me go quickly here. So we want to look up the endpoint. Now when I do the lookup, we need to make sure we select the right context. So here you can see I execute this kubectl exec int kind DNS1, so that's the bottom cluster. And I do this NS lookup of the Nginx service of the top cluster, and I can get the response. So this service, of course, only exists in the top cluster. We also have the DNS here. And this works for the Nginx, or of course for the endpoint 1 we had before. You can see the name. Now I want to quickly show that, of course, this also works the other way around. So I can do, let's select the context. So I have another DNS endpoint CR, which is defined here. I apply it to the bottom cluster. Maybe I can quickly show this DNS endpoint CR2. So this is basically like before, just a resource of type DNS endpoint. It defines the DNS endpoint 2 to be this target 2. And now in the bottom cluster, we can again look at the logs of external DNS 0, and you can see that if this is the wrong pod, in this pod, you can see that here you have the endpoint 2 being added. So now let's do the dig to look for it. I can check here endpoint 2, I get the response. So this was in the cluster 1, it's been applied, and now I can also do it in this top cluster, and you can see we also have it there. So the syncing now works in both ways, so everything works fine. Now I want to show you a bit the resilience of the system. For this, let's simulate that something breaks. So what we do for this is I scale down the deployment of Power DNS in cluster 0. So you can see here, the replicas, I put it to 0. So let's first go back so we see all the pods. Now when I execute this, you saw now that the Power DNS disappeared in the top cluster. And if I do a request, oh, this was the wrong one. If I do the request again here, I still get the response. So our forwarding works. And what's really nice is here I got another DNS endpoint. I got another one, endpoint 3. Let's apply this one to the top cluster. So the 3, we apply it to the cluster 0, so the one where we kind of broke the Power DNS. I add it, we can look. So you can see now the external DNS 0 went into an error mode. So this is because it tries to write in the Power DNS of the top cluster, but since this one doesn't exist anymore, it can't write to it anymore, so it's in a crashback loop. But what's nice is that there are 2 separate instances. So the external DNS 1, we can have a look at the logs. This one still continues to run. It saw the endpoint 3, and it wrote it in the Power DNS of the bottom cluster. And now we can do this, the request, and this lookup, for example, of the endpoint 3, and we have it here. So I requested it at the top cluster, which is broken, and it still worked. So that's very nice to see this, that it's still working, and just to show that this can really be broken, that this is actually a demo. I can scale down our core DNS. So this is, now I want to scale down the core DNS. So this is our core DNS at the top, which does the triage to the other cluster. And if I scale this one down to 0, you can see it's gone. If now I do the lookup of the top cluster, it doesn't work anymore. So you can see that this actually did the forwarding. Also, what I want to show quickly is the fallback to the internet. So if I search google.com, after 2 seconds, it should fall back and directly go and ask the internet, and it found it. So it's still in a working state, our cluster. So this is nice. And what's also nice about having everything KRM and Kubernetes based is I can just scale back up the replicas of the Power DNS and of the core DNS. And if I quickly remove the external DNS so it restarts faster, you can see that as soon as the external DNS gets back up, we can have a look at its logs, and it directly will detect all the resources and write them again in the Power DNS. So you can see now it created them all again, and they're all back, and I didn't have to do anything. So this is a really nice, this automation. All right, so this is the end of the demo. You'll see the link later afterwards. So this is all on our GitHub here. And there's also a script to set everything up. There's a parameter. You can also say you want 3 clusters, and then we'll set everything up for you for 3 clusters on your local machine if you want to play around with it. And with that, I'll hand it back to Joel.
Yeah. Thanks a lot. Thanks for this impressive demo. So you've just seen like a very quick introduction of how this DNS system works. Yeah, if you're interested, please check it out yourself. Give some feedback. We would be curious on your thoughts. I'm going to talk a few minutes about limitations of this system. So we think there are 3 limitations. So the first one is the self-dependence, given by the fact that we decided to use the same clusters where we deploy 5G core to serve DNS records. You can easily mitigate that by just moving out the DNS to separate clusters. Second limitation is Kubernetes resource only. So we decided to use the Kube API for all interactions. That's a given by that system. And the third one is service discovery. So we think that external DNS, the tool that Fabian showcased for the DNS records automation, is not suitable for service discovery. We have a few more details about that. I cannot go through that now. Approach us if you have more questions. On the other hand, what did we achieve? So going through the 6 requirements again, we see that proximity to consumer is solved by just the fact that it's an on-prem deployment, so we are as close as it gets. It's fully automated because we use GitOps and external DNS. We didn't showcase GitOps, but I think you get the picture on how this would work. Then it's geo-redundant, so we can run on many clusters. So how you place the clusters is basically up to you. We support the advanced resource record features by using these DNS endpoints. We can put anything that is supported by DNS in the end. Then it's fully KRM-based, Kubernetes resource-based. And last but not least, we removed the single points of failure by having independent instances. So the Power DNS database backend is not shared. It's a single database backend for each cluster, which means we can lose any of these without being in trouble. And with that, thank you very much for being here, for your interest. I think we have 2 more minutes for questions. If there are any questions, you can find the resources behind that QR code if you're interested, or in the slide deck that will be provided later. Yeah, thanks a lot. Yeah, go ahead.
I'm interested in how the scalability of your multi-cluster architecture has turned out. It looks sort of full mesh style, but everything's updating everything.
Yeah, it's full.
How does it scale beyond the 2 questions?
Yeah, so the question is about scalability of the system, and it's true. It's full mesh. So if you have 3 clusters, you're going to end up having 9 external DNS. And so on. So we use it up to 3 clusters. That's the current plan. So it is a bit of overhead. That's true. But we don't intend to use like a 16 cluster setup or anything. If we're talking about scalability of the consumer side of DNS, like the resolver, the core DNS part in this case, we can easily scale that out. But I think 3 instances is good enough in terms of redundancy, which is the goal here. Yeah.
Okay, thank you.
Yeah. Yeah.
A question more on the application. So is this like, does it says 5G core, is that the new standalone core? It's not like LT?
Yes, it's the new standalone core. Yes.
And are you supporting the Ericsson network functions, or are you basically building it up yourself?
We build it up ourselves. So this is not Ericsson provided. Yeah.
Okay. And the NARPR, this rolls, is that because you have, let's say, like the voice, all the voice stuff, like IMS on top of this?
So the goal is to start with the system with the 5G standalone core and extend it for more use cases in the long run. That's why we already looked at the use cases for instance, for NAPTER records or stuff like that.
No real network functions live at the moment?
Not in production as of now. Yeah. Yeah.
Okay. And last question.
Yeah.
How many dots? So many dots have you tested?
How many?
Dots. When there was always this issue with DNS and Kubernetes.
Aha.
Yeah, like where you have maybe, I don't know, a certain operator, like Ubuntu usually sometimes fine, but you have this recursive lookup, where if you had over 7 dots, I think, on the supplements, it would just not find it.
So the question is about how many dots in the DNS name you can have. We didn't test that, to be honest. I mean, it would be, we definitely, if it's going to be an issue, we will find out quite soon.
We can test it during the apero afterwards if you want.
So, but I think, I mean, every component on it, so external DNS, power DNS, as well as core DNS will probably have its limitations if they don't adhere to RFC. But I don't know. Any more questions? No, I think we're out of time. I don't know. For me, it's okay. Yeah, okay, one more.
So I have more of a higher level architectural question, because to me it seems like you're sharing a lot of resources between the two clusters. So one cluster is advertising DNS names to the other, and I assume that the goal is also to have the two routed together in some scenarios, of course, because otherwise it wouldn't make sense. What is the advantage of a system like this that adds more complexity compared to just having one macro cluster that is redundant between two sites? Because in that case you wouldn't need all of this system. It would just be, I don't know, stateful sets on all the nodes, and it would be immediately available from anywhere.
Yeah. So the question is why using multiple Kubernetes clusters? Why distribute it that much, right? And what's the advantage out of that compared to one big cluster? So I think it's also given by the nature of the application that consumes the DNS service, which is also built like that. It's distributed across multiple clusters. But for this architecture specifically, I see it also as an advantage because of the single points of failure. If you think one big cluster, the Kube API and the control plane of this cluster is a single point of failure. If you have an upgrade and something goes wrong because, let's say, etcd corrupted or something like that, you will lose the entire cluster, and it will be harder to control or to mitigate, right? If you know you can always lose a single cluster out of the 3 or out of the 2, it's easier to maintain. That's why it's about high reliability in the end, and that you can apply that to every component in the chain, I would say.
I got a very quick question.
Yeah.
What is the latency benefit of your solution compared to Route 53?
In milliseconds, or the latency benefit of our solution compared to Route 53. So the latency itself, I mean, you can get it down with caching, for instance. That's feasible. But it's also about proximity. Is not only about latency, but also about the network path in between, right, which needs to be reliable. And so latency-wise, I think we can tweak it with Route 53. That's not an issue. But since we're already on-prem, we're on our own premises, I think that's the biggest benefit. But in terms of milliseconds, if you deploy it in Switzerland, it's peanuts. Because as you've seen, we're in Bern, Zurich, which is, that's metro in the US, for instance. I think there's not much of a difference in terms of latency itself, All right, thanks a lot. Enjoy.